We're going to talk about the circuits lab now. Now, those of you in Physics 101L, your lab manual has this experiment start on page 110, but we really want to go to the next page, page 111, where we actually start writing things for the lab. For those of you in Physics 102 or Physical Science 103, your lab manual has a two-column format where they show a circuit diagram like mine on the left-hand side and another diagram on the right-hand side. The right-hand column you can ignore. That's for old equipment we used to have here at the college. Physics 101L, you don't even see the right-hand column because I removed it. So we do have to use our lab manual. We do have to use our lab manual for this experiment. I'm not going to email you, I'm not necessarily going to email you a document for this lab. So do use the Physics 101L lab manual if you're in Physics 101L. Physics 102 lab manual if you're in Physics 102. Physical Science 103 has a lab manual. So I had to say that for the 101L students because they are used to me emailing a document to replace the lab manual for an experiment. Before we start this experiment, I got to talk again about series and parallel circuits, which you see in your textbook, you hear about it in lecture. Here's the idea of series and parallel. In a series circuit, these two light bulbs here are said to, those are light bulbs, are said to be in series because the current that flows through one of them also flows through the other one. See? If a charge comes in here, a current comes this way, electric current, it goes through that light bulb, the same current goes through the next light bulb and back to what normally was a power supply. In this experiment, we're using an AC source, which means an alternating current. The current flows one way and then the other way. Then back the other way, forward again, then backwards again. 60 times a second, 60 cycles a second. We're using that so we don't have to be concerned about which is the positive wire and which is the negative wire and hooking up to a power supply. We don't care about that. So that's a series circuit where the current flows through, those components are said to be connected in series if the same current flows through each of them. A parallel circuit, on the other hand, is where the voltage across them, the potential difference, is the same across both components. Here's parallel. Look at this. Here's a light bulb. Here's a light bulb. The voltage up here with respect to the bottom here, notice voltages, potential differences are always measured with respect to some reference. I'll call the bottom my reference, I'll call it voltage 0 volts. So the voltage up here at the top with respect to that bottom is the same across all the components here. Look at that. The voltage across this is also the voltage across this one. They're in parallel. Can you have a circuit where the components are connected in parallel and in series? Only for really simple circuits, like, I'll do it. This is the first circuit we're going to use in today's lab. All I have to do is erase one of these light bulbs. This circuit, the power source and the light bulb are both in series and in parallel because the same current that goes through the power source also goes through the light bulbs, so that's series, but the voltage up here that's across them is the same. Voltage up here with respect to down here. Because voltages are always measured with respect to a reference, our meter has a lead that is called common, that's what the COM in the meter is about, and another one where we actually take the reading of the voltage with respect to common. But in today's experiment, we're going to use AC voltage where the current's flowing one way and then the other. And so you don't really have to care about, well, which one is the reference and which one is the reading with respect to the reference. It's going to be changing back and forth, so we'll just say, okay, the voltage across the thing, this reads what they call root mean square voltage. It's mathematical stuff. It's like almost like an average, but it's a little different. It is an average, but that's what it reads. And so we won't care about whether we have the black wire here and the red wire here or switched. It won't matter. Well, that's kind of nice. I like it when things don't matter. However, to do that, when we turn our meters on, we have to turn it to a setting, a V with a tilde over it. That tilde means AC or AC source. So we're looking at a root mean square, or engineers say an RMS voltage reading. Okay, if you did it with a V with a bar over the top, that's DC voltage, and in this lab we don't want to see that. Then you would have to be concerned about where does your black wire go from common, and where does your red wire for the reading go. We want to be able to switch them. So our power supply, let's go ahead and turn the camera down here at this transformer. And I want to show you the equipment here. So right down here is our power source. It's a transformer with a special kind of switch. The switch, if you have a short, will turn the power off suddenly. Don't try to push the switch back on and force it, because you could fry the transformer. So the transformer, it's attached by a cord to the AC outlet. The transformer brings the voltage down to, what is it? We'll find out. It's something like 7 volts or something like that. We'll see in the experiment what it is. 7 volts RMS AC voltage, where the voltage is switching which way is positive, which way is negative the whole time, 60 times a second. Now this is our first circuit, the one I just talked about that's both series and parallel. There's a power source and there's a light bulb. When you hear that some materials don't obey Ohm's law, they're not saying that the resistance and voltage and current don't obey that equation they gave you that they call Ohm's law. What they're saying is the resistance is not a constant. The resistance can vary. I'm going to turn this on. Look at that. The light bulb is glowing brightly. And we can check the voltages out now. So I'll put this up like this where you can see it. And I'm going to take my little probes. Now the way you use this, you do not hook this meter up in the circuit. You have the whole circuit running, and then you take these things here and act like little probes. You stick them in the circuit where you want to measure something. In other words, you put these in parallel with whatever you're looking at. So the voltage across these terminals is the same as the voltage of what you're trying to look at. Oh, that's right. Got to turn it on to that V tilde setting that I talked about on the board. So it's reading AC volts. And I stick it on here. It doesn't matter which way I put the black and the red, because it's AC. That component out there is putting down 7.46 volts. RMS, root mean square. If you look at page 111 in your 101L lab manual, or whatever page it is in Physics 102 lab manual or Physical Science 103 lab manual, the first circuit shows the transformer. They drew it different than I did. They actually show us a transformer. I just showed it as some AC source. And there's the light bulb. And they have these voltages. They name every point in the circuit with a number. So they say one end of this power source is 0.1. The other end of the power source is 0.2. Which is what? 1 or 2? Doesn't matter. Call either one 0.1 and the other one 0.2. We're doing AC voltage here. Okay? And so when it says V12, it means the voltage between points 1 and 2. Which one's the reference and which one's the reading? Doesn't matter, it's AC volts. So for V12, you'd write down 7.45 or 7.46, whatever your meter says. Mine's changing. It says it's 7.44 now. Oh, I know why. The light bulb's getting hot. That's why. It changes things. Look there, it says V34. Let's see, points 3 and 4 in the circuit are across the light bulb. Whichever one you want to call is 0.3 and the other one's 0.4. So I'll take my probes for the meter. Notice they're outside the circuit. This meter has what they call a high impedance or high resistance, so it does not affect the circuit. If it had a lower resistance, it could affect the circuit by drawing current away from it. It has a really high resistance, so it doesn't affect the current. It doesn't affect the thing you're trying to measure. Let's put it in. Oh, it's the same voltage. We would expect that because remember, this circuit's not only series, it's also a parallel circuit, so the voltage should be the same. It's, again, going between 7.44 and 7.46, just like it was the other one. Well, but if you look at the sheet, it asks for V12, which we measured first, the voltage across the power source, V34, the voltage across the light bulb, and then there's a thing where it says bulb X. That's the bulb X. What it wants to know is a rough indication of the current to the light bulb. Are we going to measure the current next? No. That's more involved. That's a more advanced laboratory technique. And it would slow us down to do it. So rather than that, they want you to tell the current of the light bulb by a qualitative index. You either say the bulb is off, the bulb is dim, or the bulb is bright. That right there is bright. Should look bright in the video. See that? Bright bulb. Okay? To show you what a dim one would look like, I'm going to take and do the very next circuit. On that same page in the lab manual, they want you to do a circuit where you go. Let me get the meter out of here first. Take the meter out. So the meter should be out of your circuit while you're hooking it up. And they want us to take and put the current through 2 light bulbs. Now we have 2 light bulbs in series, so the same current goes through each of them. Look at that, they're dim. So in the next entry down there, where they show circuit number 2, shows 2 light bulbs in series. See how that wire goes, what goes through this one, goes through the wire, and goes through the next one, same current. They want you to take, where it says bulb X, they call this one bulb X. Well, either one you would call bulb X. I'm going to call this one bulb X. And they want you to say it's dim. That's the way you're going to indicate the current. And the next one, bulb Y. Well, if I call this one X, I better call this one bulb Y. And it's dim. If you run into a situation like this, what is the out? There's bright, there's dim, and there's off. I just pulled a plug out. Okay? There is one circuit we're going to do more specification of the current on. We're going to say dim or very dim. Just one circuit. You'll see that later. But every other circuit is going to be bright, dim, or off. Well, we better measure the voltages in here. So on the page there, the first pages of where they show the circuits in the thing, for this first one you had that 7.45 volts, somewhere around there. You wrote down for the voltages, you wrote down the bulb was bright. For this circuit, for both bulbs, you put down dim. And let's get the multimeter out and see what the voltages are. The first voltage they want you to measure, which they call V12. Oh, it's across the power source again. Doesn't matter whether I put the black wire on this side or that side, so I'm going to do the red one on the other. Well, the power supply is still 7. Oh, it's a little different. It's 7.56. Man, I guess the light bulbs are getting hot or something. I don't know. Well, we'll think about that why later. 7.56 volts. Okay. Let's look at now, what's the next voltage they want you to measure? They want you to measure V34, which they claim is the voltage across bulb X. This be 0.3 and be 0.4, or the other way around. The voltage is 3.93 volts. Well, 4. 3, 4, it keeps oscillating there. 3.93 volts. And they want you to look at the voltage next, which they call V. (5.6). Well, I had to change meters. My meter's battery was getting low. Let's go back to the circuit number 2. Let me check those voltages again. So, first one they want you to read is V12, which in the diagram shows it's across the power supply. (7.55 volts). Okay, that's V12. By the way, while we're at it, bulb X and bulb Y are both dim. So where it says bulb X, you write dim. Where it says bulb Y, you write dim. And this is the voltage we'll take for V12. 7.55 volts. The next one it says is V34, which it says is across bulb X. In the diagram it says that. So I look at it, and the voltage is 3.98. Whoa, what's causing that spiking? Just make sure I'm not shorting anywhere. Okay. The next one it says is they call it V56, is across bulb Y, and it is 3.46 volts. That should add up to about approximately the voltage of the power source. Might be a little bit off because, well, the bulbs are heating up and wires may have some resistance in them, but that's very small. Okay. Now, there's one more voltage they want us to measure. They call it V36. 0.3 is on one side of bulb X, and 0.6 is on the far side of bulb Y. So you're looking at the voltage across both bulbs. Those of you can probably predict what's I'm going to get. Yep, sure enough, 7.5, well it says 4 volts. Let's see, has anything changed? That last measured V12? Yeah, it's also 7.54 now. Whoops, now it goes 7.55. Okay, it's off by a little bit. Yeah, 7.54, almost 7.55 for V36. The reason you expect it to be close to the voltage of the power source is because, well, those bulbs, even though they're in series with each other, the combination of bulbs is in parallel with the power supply. Should have the same voltage. Of course, wires could have some resistance in them. All right. The next circuit they want you to do, and I'll turn the power off just because that's good practice, is they want you to put them in parallel. Okay, and that is circuit 3 in the diagram. I'm wrong. It says circuit 3 we're supposed to do, back to the circuit we got. You turn the power back on. They want you to do one change to that circuit, change circuit 2 to make it circuit 3. They want you to take bulb X out. Really? Let's do that. As you might expect, well, bulb X isn't even there. Bulb Y is off. Wonder why. So, They still want you to measure the voltages though. Now you say, well, there's no current. How could there be any voltage? Of course there could be. And they want us to check that. The voltage across the power supply, the power source, is about 7.80. Whoa! See, this power supply is not perfect. The more you try to drain current from it, the voltage is going to drop. And if you don't drain a lot of current from it, the voltage is going to rise. So there's still a voltage across the power supply. It's clear up to 7.80 now. What's the next voltage they want us to measure? By the way, bulb Y you say is off. V12 was 7.80 volts. V34 across the place that bulb X was supposed to be, but it's not. We took bulb X out. But we still look at the across here where it was going to be. And wouldn't you know it, there's a voltage there. 7.80. That's bobbing between 7.80 and 7.81. Well, our multimeter is not perfect. What's the next one they want us to measure? The voltage 5.6, which they say in the diagram is the voltage across bulb Y. Well, there's 0 volts. You kind of expect that. There's no current flowing through the light bulb. Okay. The light bulbs are kind of like resistors, just that the resistance varies. It doesn't stay constant as you turn the current up. And the last one they want us to measure is V36, which means we measure all the way from the place where bulb X had been connected all the way to the other opposite end of bulb Y. And of course you're going to get 7.80 volts, the same voltage across the power supply. You look at the diagram, you can kind of see why that should be. Are we going parallel yet? Nope, not quite. They say put bulb X back in. Oops. Where's the power? There it is. There's a lead from the power supply. And this wire was here. And it's back to what circuit 2 was. But they say, make one change. Short bulb X. What that means is, take a wire. Doesn't have to be a short wire. And go from one end of bulb X to the other side. So the current, instead of going through bulb X, will go through the new wire I'm adding. So all that current goes through the new wire, not through bulb X. Bulb X is off. Bulb Y is bright. Oh yeah, bulb X you put down off. For bulb Y you put bright. And let's measure a voltage. Let's take our, well, I'm getting things tangled here. The first one they want us to measure is V12, which again they say is across the power supply. And we get 7.44 volts. That's pretty close to what we had in circuit 1 with just one light bulb. It's 744, 745, it keeps bobbing between the two. Shows our multimeter back then was working despite the low battery thing. Next one voltage they want us to measure is V34, which is across bulb X. You got an idea what that's going to be, right? Could be 0, but look at that, it's 0.03, showing that there is some resistance in this wire that I used to short it. If this was with a perfect conductor, this wire here, that would be 0.000 volts. But it's not. Okay, so when you're there, you can actually put down 0.03, but you know it should have been 0. What's the next one they want us to measure? V56, which they say is the voltage across, in the diagram it shows it being the voltage across bulb Y. Well, we get 7.42. You're saying, why wasn't it 7.44, the voltage of the power supply? Remember, we just showed that there's some resistance in this wire here. Not the best wire in the world. Well, how about that? We find things out about our wires. Most of them are better than that, but they're not all, none of them are perfect. Okay, so that's what do they call that one? 5.6. Then they want you to measure the voltage 3.4, which is clear from this end of bulb X to that end of bulb Y, and of course it's going to be 7.42 volts again. Yeah, that's odd. 7.43 volts. That's okay. So, man, I'm going to wonder if it's really the resistance in this wire is so low, or is our multimeter not perfect? That's okay. Write that down. Write down what we get. 7.43 volts. That was circuit 4. Now we get to have some fun. Here is an experiment. We're going to actually be able to say off, dim, or bright for the bulb. We're going to have to say things like dim or very dim, because we're going to bring a new gadget in here. We're going to bring a potentiometer. Okay, well, our sound system is kind of going out on our video equipment here, but I was about to show you what a potentiometer is. Can't really see by looking at the thing there, it's all sealed, but I'll show you what a potentiometer does. I'll show you some that where it's easier to see what they do. Potentiometer, in our experiment, we're going to use it like a variable resistor. We can dial the resistance value. They're really a 3-terminal device. You see there's 3 terminals on the potentiometer, but 2 there and 1 here. This yellow one here corresponds to this center connection here, and you can move that up and down across the resistor. The resistance from here to here, when this is not connected to any circuit or anything, the resistance is constant. But the resistance from this point here to there can be adjusted. This thing can actually slide. Here, I'll show you a physical potentiometer. Like, see here, here's the 2 terminals you see, the top and the bottom here. And then this terminal here is attached to this feeler that actually is on that slide there. So this thing slides to adjust the resistance from here to there, or from here to there. If this thing slides all the way to the bottom, the resistance between these 2 points decreases greatly, whereas it increases between this point and there. Likewise, if you slide this one to the top here, the resistance here goes small, and the resistance from here to here gets larger. But we're only going to use 2 terminals, so this becomes like a variable resistor. Oh, here's another potentiometer. Here you see this dial here turns the little feeler along the back of here. Down here are the 2 attachments to the outer terminals that you see up there, upper and lower. The center one is attached to right here, attached to that little device that goes along there and adjusts the resistance. We only need 2 terminals. All right, and so what we're going to do is we're going to hook up 2 terminals then. And let's see, you hook 1 terminal to the yellow center, 1 terminal up to either one. You choose one of the orange ones. We're not going to use the 3rd terminal. Okay, and we're going to hook up the circuit that is circuit number 5 in the lab. Circuit number 5. Okay, we're going to do that. Okay, and as you see, I can make it so those bulbs glow dimly. This is very much like circuit number 2, except we added this potentiometer. Okay, or I can turn this and make it very dim. What happened? They're still glowing, but it's so dimly, I don't even know if you can see that on the camcorder, but they're actually glowing. What I did was I used this like a variable resistor. When I put it in this position, it's a low resistance. So it's just about like circuit number 2, where you just had 2 light bulbs in series. But when I turn this knob, it makes it a higher resistance here, large resistance. The current goes down in the circuit and makes the light bulbs become very dim. So this is the one place, if you look at the tables for circuit number 5, they have a column for small resistance and a column for large resistance. The column for small resistance is when it's dim, and the large resistance is when it's very dim. Well, if we measure it with it bright like that with a small resistance, and I take this multimeter and I probe, of course we're going to get very much like we got in circuit 2, very close to it. .44 volts, so that's V12. What are bulbs X and Y? They're both dim. Okay. For V34, which is across bulb X, we get 3.66 volts. For voltage V56, which is across bulb Y, we're going to get 3.57. Hard to say. And what's the other one we got to measure? Voltage 3.6, which is where I take this one, put it clear over here, and I should get just about what I get for the power supply almost. Oh, no, not quite. I forgot there's a potentiometer in there. It has some resistance. So 7.37 volts. And the last one they say measure V1011, which by the diagram is across the potentiometer. And I get 0.00. No, a small voltage, 0.125 or something like that. It's moving. No, maybe I should say 0.12 volts. Two significant figures, 0.12 volts. Okay, let's make the resistance more significant in the potentiometer. So you got those for that small resistance column, dim, bulbs, the voltage I said. Let's take and change the resistance down to where they become dim. Let's look again at V12. .61 volts across V34, which is across bulb X. 1.56. Don't go with four significant figures. It's 1.56. Bulb VV56, which is bulb Y, is about 1.29. Whoa. Well, as the bulbs get hotter or cooler, well, 1.2 volts anyways. And across the potentiometer, V1011. I missed one, I know. I'll get back to it. 4.84. Remember, this was really small before. 4.85. And we forgot to get to this one here across both the light bulbs, which is the V36. That's 2.78. 2.78. There's going to be discussion questions about that circuit right there. That's quite interesting. Okay. Now for circuit 6, we finally put the light bulbs in parallel. This potentiometer is out of there, and we're going to do it this way. We're going to take and connect the tops of these light bulbs, connect their bottoms, and we take the other end of the power supply. See how these are in parallel? Same voltage would be across them because the voltage applied to the top here with respect to what we have at the bottom. Of course, it's AC, so it's changing back and forth which one's lower and which one's higher. They're both bright because, let's find out why. Let's start measuring voltage. So the bulb X and bulb Y are bright. That's what you put down there. For V12 is the voltage across the power supply. The voltage is 7.15. That's lower than we had before, isn't it? They'll ask about that in discussion questions. 7.15 volts. What about across the bulbs? You kind of know the answer already, don't you? V34, 7.13 volts. V56, is that what it's called? Yes, across bulb Y is 7.13 volts. Let me check that power supply again. .145, that's 7.15, that's what we have before. Okay. Yeah, that's interesting. It drew more current from this power supply, didn't it? Hey, notice the voltage was lower. Transformer cannot put out an infinite current, can it? So you draw more and more current, the voltage is going to go down. Yeah, that's like one of the discussion questions asked about that. Okay, well, they got to try something. Circuit number 7, they say, let's have that same circuit we had in circuit 6, but let's take one light bulb out. When we did that with series, everything went black. Here we're going to do it in parallel. We take one bulb out, so it's gone. Hey, the other one stayed bright just like before. Interesting thing about parallel circuits. I take a component out, it keeps on burning the other one. So they want to know, this bulb X, of course, is bright. There is no bulb Y in the thing. V12. This circuit becomes very much like circuit number 1, doesn't it? So we should see the voltage is 7.48 volts. The other voltage it wants to know is across bulb V34, which is across the bulb. Of course, it's going to be 7.47, very close to 7.48. Okay. Let's do a different thing. Let's go back to what we had in number 6. We have another light bulb in here. And they want you to take a wire and short the thing. Which one do they want to short? In circuit number 8, they say short across bulb Y. But wait a second, bulb Y? If they're in parallel, it should do them both, right? Listen very carefully to a sound you might hear. Unfortunately, our sound system is going bad here. So let's see if you can hear it. The thing turned off. The safety device on here turned this thing off because we were drawing so much current. We didn't want to melt the power supply. We didn't want to melt the transformer. So a safety device in here turned the thing off. Don't try to force it back on. Nope. It's supposed to do that. Well, what kind of voltage are we going to measure now? You got to know. With the whole circuit shorted, the voltage should be 0. So let's check it, make sure that's true. We'll take this, we'll check the power supply, we know. 0. We'll check the bulbs. 0. We'll check the other bulb. 0. Of course, she said, well, of course, the power supply shut down. The power source shut down. Well, so the voltage is all there in that part for circuit number 8 are 0. Let me take the short out of here. Is that the short? Yeah. I'm going to turn the power supply back off. Now we're clear back to circuit 6 again. Well, that's interesting they did that. So far, everything we've done has been series or parallel. We maybe put a potentiometer in there. We did shorts. We took a bulb out. We did all kinds of things like that. But we were all starting with a basic series and parallel circuit and then modifying it by shorting something or taking a bulb out, putting a potentiometer in there so we could be like a dimmer switch, a dimmer. Now, starting with circuit number 9, we're going to build some circuits that are neither series nor parallel. That doesn't mean there's parts that aren't parallel or parts that are in series, but the circuit itself is too complicated to be either series or parallel. Look at circuit number 9 in your lab manual. I think the numbering of the circuits is the same in all 3 lab manuals, 101L, 102 lab manual, and Physical Science 103, I think all have the same numbering of the circuit, so we should be looking at the same circuit. We start off with 2 bulbs in parallel, but there's another bulb that's going to be in series, sort of with that combination, and with the power source. So we're basically going to take this thing from the power source. I need to bring another light bulb in. And I'll put it in series with those. And what we see is a I'd call that bright. These dim or very dim, but we're just going to say dim. The only place we had to use the adjective very was on circuit number 5 because we had to. Now we'll just say, okay, this is this bulb here. This is our bulb X now. I know that was our bulb X, but I changed it by changing the order of the bulbs. If you look at circuit number 9, bulb X is this one. The two bulbs that are in parallel with each other are bulbs Y and Z. Bulb Y and bulb Z, I'll call it. And so they want us to measure the voltages again. So I'll take our probes and we do the usual. V12 is across the power supply. .52 volts. Bulb X is our new bulb where we added. Hope the bulb is like the others so it doesn't change characteristics too much. 5.96 volts. Bulb Y, this one, used to call it bulb X, but I changed the circuit. Bulb Y, the voltage is 1.56. I want to get 3 significant figures there. It's one of the things with light bulbs, things change on you. It's not like a regular resistor. Bulb Z, 1.575. Let me check the other bulb again. Oh. Yeah. Let's find out. The other bulb was 1.56. Yes, our wires do have some resistance in them. Why I say that, you expect the voltage across these 2 bulbs should be the same. They were pretty close, but because there was a little bit of deviation that the meter was seeing, it showed me some resistance in our wires. Okay, so that's circuit number 9. What voltage did I miss? I measured V12, I measured V34, which is across bulb X. I measured V56, which is across bulb Y, and a V78, which is across bulb Z. So bulb X is bright, bulb Y is dim, bulb Z is dim. Now, okay, what is the difference between that and circuit 10? Circuit 10 is the exact same circuit, but guess what they're going to do is have us do? We're going to short something. Oh man, are we going to have the power supply shut down again? Well, let's see. What are they having a short? They're having a short bulb X. So I take bulb X. This will make it so no current flows through bulb X. Oh, look at that. Bulbs Y and Z went bright, and bulb X, there's nothing because the current's all going around it. All the current's going through the wire. Well, if there was no resistance in the wire, that would be true. All the current goes where there's no resistance. And so that's pretty much what you see. Look, bulb X is off. Bulbs Y and Z are bright. Let's look at the voltages. You want to make a prediction as what you're going to see? It's okay, you can pause the video if you say, I want to make a prediction. Well, V12, why you can make a prediction. What circuit does that look like now if we short this one out? V12 is 7.13. We saw that before. 7.13 volts. We saw that before in a circuit. Let's take a look at what the voltage across V34 across bulb X is. As you kind of suspect, it's really low. It should be 0. It's 0.007 volts. Why 0.7? Oh, our shorting wire isn't really a perfect conductor, is it? And so now we take the bulb Y, which is now V56, I think it is, 7.10, and across Z, which is V, what do they call it? V78, 7.10, actually just saying, yeah, 7.10, okay? Yeah, it should make sense the ones that are in parallel should have the same voltage. Well, how about that? So now, in circuit 11, they're going to have us do the same thing except shorting a different bulb. Instead of X, they want us to short bulb Z. So all the current is not going to flow through bulb Z, it's going to flow around it, but look, these are in parallel. That drops the voltage across this one to 0, must drop the voltage across this one to 0. And look at this, bulb X is bright again. Wait, it was before. Okay, but here, bulb X is bright. And bulbs Y and Z are off. Well, let's take a look at the voltages. This one is almost like circuit number 1, isn't it? Look at the voltages. 7.48 volts for V12. For V34, which is across X, 7.47. Man, it's almost the same voltage as the power supply. If the wires really has 0 resistance, yeah, you'd probably say it would be. Across bulb Y, the so-called V56, just about 0. It's 0.005 volts. Across bulb Z, 0.003 volts. Now, that shorting wire is not perfect, is it? Well, that was circuit number 11. Circuit number 10, they say, get that shorting wire out of there. So we get back to the previous circuit we had. It's very much like circuit 9 now. But they say now, wait, which one am I on? Yes, that's right, circuit number 12. Now they say take bulb X and just pull it out. Everything's off. Bulb Y, bulb Y and bulb Z are off. Let's look at the voltages. The voltage is 7.81 volts on V12 across the power source. There is no bulb X, so I got to measure but they want me to measure V34 anyways across the place where bulb X was. So bulb V34 across the place we took bulb X out. There's a voltage, 7.81 volts. V56 across bulb Y. Very small voltage, 0.000, boy. And across, what do you suppose is going to be across bulb Z? 0, 0, 0. Okay, it's really down there, 0. Well, for the last one, we want to put bulb X back in. Where's bulb X? What did I do with it? Ah. Hope that's bulb X. Now we're back to like we're in circuit number 9, but they want us to remove bulb Z. Well, man, that... Oops. There's one thing I forgot, though. Yeah, I got to keep connected to the power supply. Okay. Man, that's almost like circuit number 2 again. If we take Z out, so we take the voltage and measure them. Okay, so let's take and do V12, 7.56 volts. V34, which is across bulb X. By the way, notice the bulbs are dim. I forgot to say that. Bulb X, bulb Y are dim. Bulb Z is not there. Across bulb X, V34 is 3.64 volts. V56 across bulb Y is 3.9, that's 3.89 volts. 3.89 volts. Whoops, now it's 3.91. I'd say 3.9. Two single figures about. Wait, which one did I miss? Is there any volts I missed there? They want us to also measure V78, the place where bulb Z had been. So we want to take and go, let's see where it is. It's right here. And bulb Z was connected to this end. Well, it's going to actually be 3.92 volts. And the bulbs are dim. Let's look at the discussion questions. Where are they? Oh, here they are. So, let me shoot up here. This is good. In circuit number 2, why were the bulbs dim instead of bright? Circuit 1, they were bright. But the thing was, we had two bulbs in series. And so they're kind of like resistors that just don't stay constant. And so the voltage dropped across the first bulb. And so the idea was there's a higher resistance with two of them. With the same voltage on the source, the current should be smaller. Therefore, they're dimmer. With number 2, the next question is circuit number 3, the voltage was observed between 3 and 4, but not between 5 and 6. That was the one where we took a bulb out so we saw a voltage here, but there was nothing in 5, 6. Well, look at that. Even if there's no current flowing here, there is a voltage across this thing. No current flowing here, so the voltage would be 0. Here, there's no current flowing. See how I say that right? If this acts like a resistor, there's no current flowing across the resistor, the voltage across is 0. Here is an open connection. We have a voltage being applied to the top. There's no current flowing here, so the voltage here and here is the same. The voltage difference here is the voltage across the supply, barring resistance and wires and such. So that's why you see the voltage of the supply across here. You don't see anything here because no current's flowing across that light bulb. Is acting kind of like a resistor. Okay, and so the answer there is there's no current flowing in the bulb Y. In circuit number 4, why is bulb X out? That's the bulb we shorted. We took the light bulb and we shorted it, putting wires across to short it. The reason it was out because no current flowed through it. The current flowed around the short wire. That's why, so no current flowed in. In circuit number 5, the bulbs were dimmest when the resistance in the potentiometer was greater. And we expect that. We're adding more resistance to the circuit. The voltage stays the same. From the supply it is, the current should go down because we're increasing the resistance in the circuit by turning the potentiometer up to a large resistance. Okay. And then in circuit number 6, the power supply was less than any other circuit. Remember I mentioned that. When circuit number 6, we didn't have the light bulbs in series. That was the first time. That was the first time we took the light bulbs and we actually put them in parallel. What does that do? That allows 2 paths for the current, whereas every circuit before that we had 1 path for the current. Now with 2 paths, more current can flow for the same voltage. Okay? Whoops. And so now there's more current can flow for the same voltage. Well, more current flows. This supply, I said, that transformer cannot put out an infinite current. And if there's more current you drop, the voltage has to drop eventually. Remember, you learned that power is current times voltage. So if the power source can only put out a certain amount of power, if you draw more and more current through it, the only way it can keep up that kind of power is if the voltage drops. So it's not a perfect voltage source. It keeps a constant voltage no matter what. Real voltage sources, you draw enough current, the voltage goes down, causing brownouts in cities when too many people turn their appliances on and such, despite that the power plant is really working hard. In circuit number 9, the current, compare the current in bulb X with the current in bulb Y. They didn't ask you why. Just remember there that in circuit number 9, make sure I got the right one. Circuit number 9. That was when we had a light bulb up here. Bulb X was up here. There was a current flowing in this light bulb and it was dim. There was a current flowing in this light bulb, it was dim. But the sum of the 2 currents was flowing through bulb X. That's why bulb X was bright. What they asked you the question is compare them. You're supposed to say, the current in bulb X was larger than the current in bulbs Y and Z. The question would be great if they just asked, why? You'd say, well, because some of the currents that flow through bulbs Y and Z is the current that flows through bulb X. Basically, all the current that flows out of the power source flows through bulb X. When it gets here, it divides, and half of it goes through bulb Y, half of it goes through bulb Y. That's why if you look, if you sum the current, sum the voltage across this, sorry, I said that wrong. I started to say if you sum the voltages, that's not right. That's for series. If you sum the currents here, you would get the current that goes through bulb X. We didn't even measure that though very precisely. We just measured current as off, dim, or bright. So we don't really see that. The next question is asked, in circuits 1, 4, 6, and 10, all the bulbs were equally bright. Circuit number 1, there was one bulb. In circuit number 4, whoops, it's over here. Circuit number 4, we shorted a bulb out, so again there was like one bulb there. In circuit number 6, we put the bulbs in parallel. So so far in each of the 3 cases, the whole voltage of the power supply, the power source, was across the bulbs. All the bulbs that were there. There was one bulb in circuit 1. There would have been one bulb in circuit 4, except we took in circuit 4, we shorted one bulb, so there's one bulb. In circuit number 6, we took and put bulbs in parallel, so each light bulb had all of the voltage of the power source across it. What about the last one it asked about though? It asked about, and also circuit 10. In circuit 10, whoops, where's circuit 10? There's circuit 10. In circuit 10, we had 3 bulbs, but we took that one up there and shorted it out, so again it was like circuit number 6 again. Now, so in all those circuits, the full voltage of the power source was across the bulbs that were glowing brightly. There's one more question I think on the sheet. Would you describe circuit 13 as series or parallel? Circuit 13, we took this circuit here and just took one bulb out. Are those in series or parallel? Well, let's see. Do they have the same voltage across them? No. Do they have the same current? What current flows through here, flows through here, flows through here? The same current flows through both. They are in series. When we took this bulb out, we made those in series. What was it before we took it out? Just didn't ask that in the question. Before we took it out, we have 3 bulbs. Are the 3 bulbs in series? No. Are the 3 bulbs in parallel? No. They're not in series or parallel. Well, these 2 here are in parallel. The combination is in series with that bulb. But the whole circuit, you can't say all 3 bulbs are in series or all 3 bulbs are in parallel. They didn't ask that. They just asked when you remove one bulb. Oh, now they're in series. That looks like circuit number 2. We made it like circuit number 2. Well, that's an introductory circuits lab. There's a lot more to learn. If you're really interested in change your major to, those who 101L, change your major to physics or engineering, you'll get more of that. Yeah, but now you have enough to know what's going on in your house. When the electrician comes out and says, well, these switches are in parallel. How about if I connect them in series? You can say, no. Okay? And so we learned something we can actually use in a household. There's a lot more to learn about circuits. That's the end of this lab.